We're going to switch gears now, and instead of looking at properties of solutions of linear systems, we're going to look at properties of matrices, and specifically we're going to focus on three common operations we do with matrices and some of their corresponding general properties. The motivation for wanting to do this is we're often looking at matrices that really have nothing to do with linear systems. Okay, so for example, when we're doing a change of variables and a integral, or we're looking at something like a principal component analysis sort of problem, the matrices that are involved there really have nothing to do with a linear system. And so let's start off by looking at the inverse first, and we've already defined what the inverse is. And so now we want to state 5 properties of inverses, which we're going to prove. We're going to prove first that the inverse of a matrix is unique. It follows from this first statement that the inverse of a matrix is the original matrix. And the reason why is that A is the inverse of A inverse, and therefore since the inverse is unique, it must be the inverse of A. So we've just proven the second one, given that we know the first statement's true. If A and B are both invertible matrices of the same dimension, the inverse of their product is the product of their inverses in reverse. And this follows directly from just doing straightforward multiplication and using the fact that B inverse times A inverse times AB will give us the identity matrix. Therefore, it's the inverse of AB, and since the inverse of AB is unique by 1, then B inverse A inverse must be equal to the inverse of the product AB. So 2 and 3 both follow from 1. If A is invertible and K is a non-zero real number, the inverse of a scalar multiple of a matrix is equal to the reciprocal of the scalar times the inverse of the matrix. And again, this follows from property 1. You can easily show that 1 over K times the inverse of A when multiplied by Ka will give the identity matrix. Therefore 1 over K times A inverse is the inverse of the matrix K times A, and since it's unique, it is the inverse of the product of K times A. The last statement, which is we're going to have to prove though, is that if B is an n by n matrix and it's either a left or a right-handed inverse, so here I've shown B as being a right-handed inverse, it automatically follows that B is the inverse of A. In other words, if we have an n by n matrix, we don't have to show that it's both a left and a right-handed inverse to be the inverse of A. Okay, so we're going to use proof by contradiction to prove the first statement, and so it kind of behooves us for a while to go back and think about what proof by contradiction means. So if P and Q are any two statements and we want to prove that P implies Q, a very important fact in logic is that P implies Q is equivalent to not P or Q. And you can verify that by drawing the truth tables for both of those statements, okay? But I'm going to claim that that's true. Now, the way proof by contradiction works is we assume the negation of what we want to prove. So what is the negation of P implies Q? Well, it's the negation of the statement not P or Q. So when we negate an or statement, we get an and statement, and we negate both of the component statements, and so we get this result right here. So in proof by contradiction, we start off by assuming P and not Q, and then we show that it leads to a contradiction. Okay. So we suppose that the negation of P implies Q is true. We show that it leads to a contradiction. Therefore, it's false. Therefore, its negation is true, and its negation, of course, is not P or Q, which is true. And since not P or Q is the same as P implies Q, this proves that P implies Q is true. So this is a structure of how a formal proof by contradiction works. So let's go ahead and apply that now to prove that the inverse of a matrix is unique. So we want to prove that if B and C are both inverses of the matrix A, then B is equal to C. We're assuming these are all n by n matrices, okay? So we start off by proof by contradiction. So we're going to suppose the if part, B and C are both inverses of A, And we're going to negate the then part, or what's sometimes called the consequent. And so we're going to suppose that B is not equal to C. And let's show that leads to a contradiction. So first we can look at the product BAC, and since matrix multiplication is associative, we can group it so that it's the quantity B times A times C. And by hypothesis, B is the inverse of A, so B times A gives us the inverse times C, which is equal to C. Similarly, we can regroup the product BAC to be B times the quantity A times C. Again, by hypothesis, C being an inverse implies that A times C is the identity matrix, giving us B times the identity matrix, which is B. And so the product BAC is both equal to C and equal to B, from which we conclude that B is equal to C. But this leads to a contradiction. This contradicts our original hypothesis that B is not equal to C. Therefore, our original statement was false, and the negation is true, from which it follows that if B and C are both inverses of A, then B has to be equal to C, thus proving that any two things that are inverses of a matrix have to be the same thing. That ends the proof. Okay. Now I want to prove the second statement, that if we have a one-sided inverse of a square matrix, it's also the inverse of the matrix. Okay. So this is the statement that we want to prove. So let's suppose that A and B are both square matrices and B times A is the identity matrix. Notice that it's sufficient to prove that A is invertible, okay? Because I can just simply right multiply both sides of this equation by A inverse, and I'll get B is equal to A inverse. How do I prove that? Well, let's consider the solutions of the homogeneous equation for A. Notice that now if I left multiply by B on both sides, on the left-hand side, B times A will be equal to the identity matrix by hypothesis. And of course, on the right-hand side, I'll get 0, which tells us that X has to be 0. And so from this, it follows that the only solutions of the homogeneous system are the trivial solutions. And we know from step 4, therefore, that A is invertible by theorem 4. This was one of the 5 equivalent statements, right? And from which it follows directly that B is the inverse of A, simply multiplying both sides on the right by A inverse, since we know that A inverse exists. Now, to really prove this theorem, we still have to show that A times B equal to the identity implies that B is equal to A inverse. Okay, either way will give us that B is the inverse of A. And I'm going to leave this as an exercise for you to do. But basically, the proof will take pretty much the same path as this one that we've just done here. Okay. Next, I want to talk about the transpose of a matrix. Okay. So the inverse of a matrix was limited to square matrices. The transpose is not. And we all know what the definition is. If A is an m by n matrix, then the transpose of A, denoted by A superscript T, is an n by m matrix, such that the ith element of the transpose is a kth element of the matrix. Okay. I'm going to define two terms here, symmetric and Hermitian. And basically, symmetric holds for real matrices. So we have an n by n real matrix. So we have a square real matrix, and its transpose is equal to itself. Then it's said to be symmetric. Okay. So notice symmetric is really restricted to square matrices. Hermitian is a little more complicated. It basically says that if we have an n by n complex matrix A, so it doesn't have to be real now, then if we take the complex conjugate of the elements, that's what this star represents here, and then the transpose, we get back the original elements. And so this quantity A star transpose is called the conjugate transpose of a matrix. Okay, so symmetric is real square, Hermitian is complex square. Okay, and now there's some properties we want to look at. Okay, The first is the one that everyone learns early on, which is that the ith row or column of A is the ith column or row of A transpose, and I want to prove that. Notice that if we fix a row in A transpose, then we know that the kth element is equal to of A transpose is equal to the kth element of A for every k. So that shows that these two vectors are the same. And this establishes that the ith row of A transpose is the ith column of A. And you can do a similar proof to prove that the ith column of A transpose is the ith row of A. Okay. The transpose of the transpose being equal to the original matrix follows from the definition. If I look at the kth element of the transpose, that is equal to the kth element of the transpose, which is equal to the kth element of the matrix A. And so this shows us that again, how do we do matrix equality? Well, every component, every corresponding component has to be the same, and this shows us that these two matrices are the same. The transpose is the sum of the transposes. Well, we start off looking at the kth element of the quantity A plus B transpose. We know that's the kth element of the matrix A plus B, and of course matrix addition is done component wise. So this is obtained by taking the kth element of A plus the kth element of B, and by definition of transpose, this is equal to the kth element of A transpose plus the kth element of B transpose. And since matrix addition is done component wise, this is the kth element of A transpose plus B transpose. Okay, we're just using the definition really of transpose and some properties of matrix addition. Okay, the transpose of a product is a product of the transposes in reverse order. This is a little more tricky to prove, and so we have to use a little notation here. So if we look at the kth element of A transpose, it's equal to the kth element of the product AB. And how do we get that? Well, we take the kth row of A times the ith column of B. Okay, but we know that dot products can be reversed. In other words, I can take X transpose Y, X transpose times Y is equal to Y transpose times X. Okay, so I can reverse these. So this becomes a transpose of this column vector B times the transpose of the row vector A. But we know that the transpose of the kth row is the kth column for A, and we know that the transpose of the ith column is the ith row for B transpose. So now we get that this is the product of the ith row of B transpose times the kth column of A transpose, which is the kth element of B transpose times A transpose. So it's a little tricky, but worthwhile going through. If you don't use this sort of notation, the proof becomes very, very cumbersome. The last one we want to prove is that if A is invertible, then A transpose is also invertible. And in fact, we can say that the inverse of A transpose is the transpose of A inverse. And to prove this is pretty easy. We start off with the fact that the identity matrix is equal to its own transpose. And we know that the identity matrix can be written as A inverse. We're taking the transpose of that whole product. And we just proved that it's the product of the transposes in reverse. And now we can simply reverse the order of the A inverse in A, and we get now that the identity matrix is A transpose times A inverse transpose. So notice that this matrix, the transpose of A inverse, is the inverse of A transpose, okay, by definition of inverse. And so it follows, therefore, that A transpose has an inverse, and since the inverse is unique, it must be the transpose of A inverse. And that proves that. I want to say a little bit about determinants. I'm not going to get into a lot of the theory because there are actually 3 different definitions of determinants, and 2 of them are relatively abstract, very useful, but pretty abstract. So I want to stick with the standard one, which we know, which is the Lagrange cofactor expansion. So I'm going to define the determinant of a matrix in a kind of recursive form. I'm going to say for any n by n real matrix, we can make a recursive definition. If n is equal to 2, we're going to define a determinant to be simply as follows. This is the standard formula that we all know. And then we're going to say if n is greater than 2, we're going to re-express the determinant as either a linear combination of the elements of the ith row, this is what this first summation is, or the ith column. Okay. Where the weights are these things called the minors of the matrix. So capital M sub ij is the minor of A, and basically it's the determinant of A where we have removed the ith row and the jth column. Okay? Notice this sign factor. It's an alternating sign factor, okay? Whenever the position is odd, this is going to be -1. And this is where we get this alternating sign when we figure out the determinant, okay? Now we define a singular and non-singular matrix as basically being a matrix whose determinant is 0 or not equal to 0. And I'm sorry, for this last should be not equal to 0, okay? So singular means the determinant of the matrix is 0, non-singular means that it's not, okay? And I'm going to state some basic properties of determinants. I'm not going to prove most of them. The first three are hard to prove actually. Exchanging a row or a column of a matrix changes the sign of the determinant. Okay. A is invertible if and only if the determinant's not equal to 0. And again, I need not equal to. I'm sorry about that. Okay. And this was one of the 6 equivalent statements, which we didn't deal with the determinant portion, but now we're going to bring this in as a formal statement. The determinant of a product is the product of the determinants. Okay. And since the determinant is a scalar, it doesn't matter the order in which we multiply these, right? It tells the determinant of BA is the same as the determinant of BA, of AB, sorry. Now here are some that we can prove actually. We can prove that the determinant of the inverse is equal to the determinant of A, and then we take the reciprocal of that. Okay. And you should prove this. This is actually an easy, this follows from the third statement. Okay. The determinant of a scalar times a matrix is equal to the scalar raised to the nth power times the determinant of A. It's true for every real number k. And again, you can verify that by induction. You can prove that by induction. And I would suggest that you do so. Okay. The determinant of A transpose is the same as the determinant of A. Again, this is something that you can prove, and it basically follows from the fact that we can do a cofactor expansion with respect to a row or a column. So if we did the cofactor expansion with respect to the first row of A, we could do the same cofactor expansion with the first column of A transpose. But again, convince yourself that you really believe that. Okay, multiplying a row or a column of any matrix multiplies the determinant by k, and you should verify that. You can prove that. That follows directly from the cofactor expansion formula for the determinant. If either a row or a column of A are all zeros, the determinant is 0. Again, follows from the definition. If we add a multiple of one row to another, it doesn't change the determinant. This also follows from the definition, and this is worthwhile proving. It's one of the most important properties of determinants actually. Okay? So I should just mention real quick, all of the blue statements you should be able to prove, okay? The first 3 red statements are a little tricky to prove. Okay, some applications. There's 3 that we're most interested in. The first has to do with the volume of a parallelepiped, okay? So this is basically a polytope that ends up having, basically with the edges are vectors, okay, of the polytope. And it turns out that the volume contained is equal to the absolute value of the determinant. Okay. Now in this case, we've just taken the determinant, not the absolute value, because these vectors are correctly ordered. Okay. We know, for example, this is what we call a scalar triple product. So you can see here that A dot B cross C should give us the right sign. Okay. This is also true in higher dimensions. Okay, so the volume of a parallelepiped is actually, in n dimensions, is the absolute value of the determinant of the edges of the parallelepiped. Okay, and a parallelepiped, again, is just a polytope, which is a closed convex figure whose faces are polygons and they're parallel. Opposite sides are parallel to each other. That's all it means. There's a very important corollary that follows from here, which is that if you have in an n-dimensional space vectors that embed in a space of lower dimension, like for example in 3 dimensions all of the vectors lie in a 2-dimensional space, the determinant is 0. And that's due to the fact that the volume in that space is 0. So if you have, for example, vectors in a 2-dimensional space, they basically form a parallelepiped of 0 volume. And this generalizes to higher dimensions. This is actually a very important theorem. It's called the Cayley-Menger theorem. It says if in n dimensions you have a collection of vectors that embed in a space of lower dimension, their determinant is always 0. Okay. Another important application is when we're solving linear systems. So you saw Cramer's rule before. Okay, if we want to solve for x's, each of the components is equal to the determinant of AI, where A is basically the original coefficient matrix, where we replace the ith column by B, okay, divided by the determinant of A. And of course, we were able to get the inverse of A again using determinants, okay, because we first formed a cofactor matrix, which was basically the minors associated with each element that were signed appropriately. And then we defined this thing called, it has a bunch of different names, the adjugate, the adjoint, the adjunct. I call it the adjoint, which was a transpose of the cofactor matrix, from which we were able to determine that the inverse is equal to the adjoint divided by the determinant. This is not so easy to prove. Okay, you can show that the diagonal elements give ones, but showing that the off diagonal elements will give 0 when you multiply by A is actually hard. Okay, the last property that we're going to use in our next section is change of variables. So very often with probability densities, we're going to want to change variables. And so we may have, for example, some sort of real valued vector function. In our case, it'll be something like a multivariate normal distribution, okay? And we want to integrate it over some region R, okay? And we want to do it by making a change of variables, all right? And there's a theorem that says, well, if we have some mapping from the vector u to x, which we can write as these n functions, okay, and the Jacobian matrix for that variable transformation is non-zero. In other words, this matrix, which is called the Jacobian matrix, is non-singular. Okay, easy way to remember that is that the first row is just a derivative partial with respect of g1 with respect to the different u variables. Then the second row is the partial of g2 with respect to the same variables, etc. Okay, so if these two things are true, then it automatically follows that the change of variables can be expressed as our original function, now expressed in terms of u's, these g1s and g2s, etc., are in terms of u's, times the absolute value of the determinant of the Jacobian matrix times the product of the differentials. Okay, and that's a formula that we're going to use a lot. And in fact, we did it before. We looked at the bivariate normal distribution. We did a change of variables from Cartesian to polar coordinates to show that integrating factor was you know, 1 over the square root of pi for e to the minus x squared. Okay, we're going to move on next and talk about LU decomposition in the next video.